Let's start by first setting up all the geometry that we need and then move forward with the effects. So in order to bring our camera, which is a USD asset, first we are going to have to import it at the LOPS, at the stage context. So let's hold down N and drop over to the LOPS stage. And I'll just rebuild this entire chain here over to the right. We will start with a sublayer. Let's go ahead and preview this, and I will actually rename this to, let's do just simply cam. So let's point our file to our cam USD asset, which again is going to be available in the download. So this is going to be the cam.usd. Here we have it. And we might as well just bring in our helmet USD as well. Let's just do another sublayer and let's rename this to helmet. Let's bring in our helmet.usd, and we can see, you should be seeing the textures as well. Just make sure that the texture display is on. So we can simply merge these two together, and this is what we are going to start with. If we go over here to the cam view, we should have our camera animation. So everything is working fine. We are going to later come back to this after we have everything we need, but for now this will be all that we are going to do in the stage context. So I'm gonna go ahead, because we need to reference this node. Let's go ahead and Control C, go over to the object context. So at SOPs, we'll do a LOP camera import, or rather LOP import camera, and the LOP path should be this sublayer that we have. So I'm just going to paste this here, and for primitive path I'm just gonna do a star, which is going to select the default path that we have. And now let's also do a geometry container and bring in the helmet at the sub level as well. This will be geo underscore helmet. Let's step inside and we will do a USD import, and again we are going to grab the same file, this helmet.usd, and for some reason this has some sort of animation to this, and this might be because I haven't saved this out correctly. We can see we have this green watch here that indicates that it's computing at each frame, so we don't want this. But really an easy fix for this is to just do a time shift after our node, and I will just freeze this at frame 1. And if we were to just use this as it is with this green watch icon here, this would mean that every other operation that we do afterwards is going to have to recompute, which is not optimal at all. Let's also go back to our USD import and let's unpack this and let's select polygon, so we have access to all of the attributes that we need and the primitives. We'll leave this as it is for now. In fact, I'm going to drop down a null and let's rename this to geo underscore helmets, so we can point to this later. We can go straight ahead now and create our ground as well. Let's go up, do another geo container, and this will be our geo grnd for ground. Let's step inside, drop down a simple grid, and let's show all objects. And if I press Shift W, let's increase the resolutions here. Let's use something like 200 by 200. And in fact, I'm going to use the settings that I used originally, which is a size of 25 by 25. And let's increase the rows and columns to 500 by 500. This will give us enough resolution for our initial displacement, but a lot of the detail we are going to achieve by geometry dicing at the render level. So we are going to use fractal noises from Material X to displace our geometry even further and really create those super fine details and spikes that's going to really make this material look like actual snow. But we still don't want to be working with a flat plane as far as the base geometry is concerned. So this is why we do need some resolution, so we can displace it a little bit as a base. Let's go ahead and add a UV texture to this, and the default settings will be fine over here. As we can see, you can turn on the UV display over here, so we can go straight ahead and add a mountain node. And really, I'm going to use much of these default settings. I'm just going to increase the element size slightly, and I can play around with the offset to get a better seed. So something that fits a little bit better with our geometry, something like this. Let's maybe go to our camera view and let's take a look. So I think I'm already pretty happy with this. I might want to increase the element size even more, maybe increase the amplitude, but not so much. Let's drop this down. Let's actually use 0.25. Like I said, we are going to use a lot of displacements in the material, so We just really want a good base start. Maybe just play around with the offset even more, just so our helmet is sinking into the snow a lot more nicely. So I'm just going to find a value here that works, so something like this will be fine. You can see I'm really just eyeballing these settings. There is an extra step that we have to do here by creating an actual volume out of this geometry, so it's a filled mesh. And we are going to do this a bit later when we get to rendering, because I want to show you the difference between the effect that we get if we have this extruded volume or just a simple flat grid, because there's going to be quite a difference between the two. Let's just go ahead and grab all of these layers, or rather nodes, and just duplicate them over to the side. And for this grid, I'm going to press enter and just move this back, and probably just scale this slightly. Let's also preview this as well. Let's template this so we can see both at the same time, and I'm just going to increase this. We can probably look through our camera. I'll press Ctrl 2 to switch to a dual view like so we can adjust this in the perspective and also see this in the camera view. So really I'm just going to, let's maybe drop this down slightly, and I just want to cover the size of the camera here so it's not clipped in our camera view. I can grab this mountain node and press W so we have a flat view, and let's disable the UVs for now, and I think something like this will be fine. I might want to increase the amplitude for this and increase the element size as well, and maybe change the offset. So we end up with something like this. Let's go ahead and merge these two by holding Alt, and let's drop down a null, and this will be our out GRND. And for now this will be fine. We are going to readjust some of these values when we do the rendering, like I said. But with this we more or less have all of the geometry that we need, and we can move forward and start creating the branching effects. For our branching, let's do another geocontainer, and this will be our effects underscore branches, and we will need to start with our helmet geometry. So inside our geo helmet, I'm gonna grab this node, Ctrl C, and let's do an object merge and bring this over here. Alright, and let's hide other objects, focus on this. So the problem with this geometry as it is because we have all of these gaps. So when we create a point that's going to travel across the geometry, we can imagine, for example, if there's a point over here and it's going to travel upwards, when it gets to this point, it's going to keep going over the surface, and it's going to reach this hole that we have over here, and also on the eyes as well, and in between each of these geometry pieces. We can see that there's a lot of gaps really in between all of the different components. So we need a way to fill all of these gaps. So what we are going to do is use this geometry to create a new geometry that encapsulates this entire object, and we can do this by using a bounds node. And we can see if I template this and look at my geometry, the bound node will perfectly encapsulate all of this original geometry that we have. And now we can add resolution on this bound geometry and project it back to our mesh. So from this bound node, let's do a remesh, and I'll set the target size lower here to maybe 0.02. And now we have a lot of geometry that we can fit back to our mesh. So if we do a ray from here, let's point the second input back to our helmet, and let's also remove the template display. Let's go to our ray node, and we are going to use for method minimum distance. So now we can see automatically, let's also disable show guide geometry. We can see that for the most part we maintain our original shape, and now we have this all of these gaps filled. So if we look at this and we look at the result, or maybe template this, we can see what we get. Now this is pretty good as it is, and we could use this, but I want to clean this up a little bit more. So what we can do is do another remesh after we do our array, and let's set this also to a target size of 0.002, and we can now do another array to project it back to our original mesh. So let's do another array node, and let's set this to minimum distance. So let's also turn off show guide geometry. If we compare the result of this ray to this ray, we can see that by doing a second set of remesh and ray, we get an even closer representation of our original geometry. So we can repeat this step a couple more times, and in fact, to do this easier, we can just use a for loop. So let's drop a for loop with feedback block, and I want to do maybe 3 iterations. I found from previously doing this effect that going above a value of 3 here wasn't really giving me any more accurate results. So 3 iterations should be fine. Let's place our remesh and our ray inside this repeat node, and let's arrange these so they make sense. And for our block begin and block end, we can leave the default settings here, which is what we want. Let's connect this here. And now if we look at the result, this is going to repeat the remesh and the ray 3 times, and this is what we end up with. So again, if we compare our original ray with this result, we can see that this is a lot more accurate, and we still have all of our gaps closed over here on the eyes and in between all of the pieces. So now our points, when they travel across the geometry, they won't have these gaps where they can get stuck, and they will continue their travel along the surface. So we can drop down a null from here, and we can rename this to geo remeshed. One other thing that I want to add here, and this again I know from previous experiments, I want the branches to have just a little bit of distance between the actual geometry and the branches themselves. So I don't want the branches to be right on the surface of the geometry, and for this I added a peak node here. So before our null, let's do a peak, and let's use a very small value here. Let's do something like 0.002. Okay, so I just want to push out the geometry ever so slightly. We can see as I turn this on and off, it's a very subtle difference. And again, all of this is doing is to avoid the branches being right on top of the surface, because we then risk some of the branches in certain parts be obscured by the geometry. So I want the branches to always be on top of the geometry, no matter what. And this is what the peak node will do for us. For our emitting points, we want all of the branches to start right below where our helmet meets the surface of our ground. If I do show all objects, we can see that over here, where we have this intersection, this is really where I want to start our branches to grow. So let's go ahead and grab our geo remeshed, and I will just copy this object merge over here and paste our geo remesh, so we can do this in a separate chain. So let's also grab our ground. Let's go up and let's go inside our geo ground. Let's grab our out grnd, go up, and let's bring this over here. I'll just duplicate the object merge. So now we also have our ground, and we can hide other objects. Okay, so we have our geometry, our remesh geometry, and our ground. So from here, if we do an intersection analysis, let's place our ground as the second input. This will give us all of the points of contact with the ground geometry from the helmet. So let's give this a second to compute, and here we have it. So we can already use these points as they are here as our emitting points, but we want to have a little bit more control over this. So instead, what I'm gonna do is output intersection segments, and this will create a curve from all of these points. And let's give this a second to compute, and here we have it. So now from here I can do a scatter, and I can decide now how many emitting points we want. So this will give us a lot more control this way. Now, one thing that I want to adjust here, we can see now that as these emitting points are, they are going to be right where the surface meets our helmet geometry. If I show all objects, we can see that they're right on the surface, and I want them to be just slightly below our ground geometry. So if I grab my ground geometry over here, let's hide other objects, I can do a peak node, and I can push everything down ever so slightly, so I can just decrease this position here. Let's maybe just use a very small value, 0.05, and let's see what difference this will give us if I template my original ground on top. Let's maybe use even more, so -0.1, and I think this will be slightly better. So I can untemplate this. Let's go back to our scatter result after the intersection analysis, and now if I do show all objects, we can see that they're slightly below. Maybe this is even too much. Let's go to our peak. Let's try -0.05. Okay, so we end up with something like this. I think maybe we can go even less. Let's settle for a final value of negative 0.025, so half of what we have. Alright, so here we have our points, and like I said, I just want them right below the surface of the snow. And because our material displacement will push our snow out even further, this will mean that our points will start even further below where our snow actually is, and I believe this will be fine for now. And just so I don't have to recompute this over and over, I'll just do a file cache, set this, give this a name, and let's do turn off time dependent cache and save to disk. Alright, so we have this cached, and from here we do our scatter. And the way we are going to simulate our main branches is we are going to give these points here on our scatter an initial velocity and then source them in a PubNet. So let's go ahead and do an attribute VOB from here, and I'll name this to set V. And just to begin with, I will give these a simple vector that points up. So let's go inside and let's do a constant here. Let's set this to a 3 floats, and let's do 0, 1 and 0 and plug this in our V. And if I go to the information here and click on this V, we have now this display. So this is the velocity that we currently have. Let's do a null after this, and let's rename this to out emitter. Let's set up a basic simulation with what we have so we can move forward, and I can explain things better on what we have to set up as far as the emitting points are concerned. So I'm gonna go ahead and grab this out emitter. Let's copy one of these object merges here so we can do our separate chain for the PubNet. So let's go here and I'll plug this inside a PubNet. And let's step inside here, and for our pop source we want to use all points, and let's disable the visualizer for now. So if I press play and see what we have, we can start troubleshooting every individual problem that we have to fix. So first of all, what's happening here is that we are emitting points each subframe because we are sourcing the points at each subframe. So let's maybe hide other objects here, look at our source points. And really, if we want to source only one particle per point that we have here in our scatter, this point needs to last only for one frame. So to demonstrate this, if I go back to this set V over here, and I only want these points to last for the first frame. So on the second frame and moving forward, I want these points to disappear. So we can do a switch if for this, and we can say that we can add an expression here, and we can say $f bigger than 1. If this condition is met, then we are going to basically switch to nothing, which is the same way as deleting all of the points. So if I go to the first frame, we have all of our points, and then if I move forward to frame 2, we don't have anything, and also for the rest of our frames as well. So now we only have these existing for one frame, and if I go back to my PubNet, we are only sourcing the points at the first frame. Our particles no longer keep spawning continuously. So this is what we want, because we want to simply control these points that are going to be our leading points for our branches, and use these points to then generate the trailing points that become the actual branch geometry. And let's maybe also just go back inside here, and let's go to the attributes and just set the inherent velocity to 0.2 so they don't move as fast. Okay, and this will be a good base for now. Of course, we are going to have to adjust the actual velocity attributes so they're not pointing straight up. And then inside this PubNet, we are going to create all of the logic that is going to force our particles to follow the surface of the helmet geometry. So let's go up and let's go back to our emitting points. Over here to our scatter. So the setup we currently have is spawning all of the points at the same time in our PubNet, and we are basically removing all of the points on the next frame, so we only have them on frame 1. And what needs to happen is I want to create points that's based around a region on our helmet and start to increase that region. So this will make a little bit more sense as we do it. I'm gonna go ahead and we no longer need this switch if. This is just here for demonstration, so I'm going to delete this. And let's do, after our scatter, I'm going to drop down another attribute VOP. Let's rename this to set area. and we are going to measure a distance based on a given point. And to create this point, we are just going to drop an add here and just create a point with this plus icon. And if I go to this result and I press enter, let's maybe template the scatter. And for this point that we just created, I'm just going to move this forward and a little bit more in front of our points over here. We can also hold down shift, and I also want to preview our remeshed geometry. So I want the points to start appearing from over this place, and this is why we have this second point, just so we can then control this region like so by adjusting the position of this point. So we want to reference this in our attribute op. Let's go inside, and from this op input tool we can do an import point attribute, and we are going to grab the 0 number points. So I'm going to middle mouse click on the ptnum and promote to a constant, which is going to be 0. So this just grabs the point that we created right now with the add node. So from the position of each of these points, we can now generate a distance, and we will generate this distance to this point that we created. And if I do a compare from here, so let's do a compare after the distance, and let's say if this is greater than a value here, let's go ahead and plug the result of this bool inside the CD just so we can preview this. And if I start to increase this, we turn the points that are closest to the point that we just created, so our second input, the points that are closest to that point are going to be black as I start to increase this. So we want the reverse effect, and let's set this to less than. Okay, so now we can see as I start to increase this, we start to add more points into the mix, and we will increase the area from which we spawn our leading particles. Now we don't really want any points, so we can see that the points here disappear, but really they're just being turned to black. So if I do a point display here, we can see that we still have all of the points, they are just being turned black. And maybe I can press D and also increase the point size here, and I can go to, let's go to the background here and set this to a light display. Alright, so now we can see a little bit more clearly what's happening as I increase this value here in our compare. Now I don't really want to spawn any points behind our mask, so if I go up and I look at my points and template my mask, or rather our helmet, I don't really want to have any points over on this side. I really just want the lines, so our primary branches, I just want them to be on this side of the helmet that's facing our camera. So if I look through the camera, we can see this here, and I pull back a little bit, we only need them over here, and we can get rid of some of these points here. So we can use a clip node for this. Let's drop down a clip, and I can turn this around and hold down Control to snap to 90 degrees, and also move this over like so. And let's choose primitives below the plane, and maybe also bring this slightly back. Alright, so if I turn this on and off, we get rid of all of these points here that will be in the back of our helmet. So let's go back to our set area, and again what we have so far is by increasing the compare number here, we increase the selection of our points. Now currently we are just turning them white, and what needs to happen is that as soon as a point turns white, I want that point to last for a single frame and then delete itself. And in order to track the time from which a point turns to white, we are going to have to use a solver. So by using a solver, we are going to be able to check for any given condition on each frame, and this is what we want. So for now, I'm going to promote the second input here. Let's promote this to the top level so we can animate this here, and I'm going to expand this region. I want all of the points to start black, so I'm going to drop this all the way to 0. Add a keyframe by holding Alt and left clicking, and I'm going to go forward maybe to frame 50. And just increase this value to a point where all of the points here, especially these ones in the back, all of these are being turned to white. So let's just increase this value until we get all of the points. So in my case 1.8 seems to be working fine. So if I play this animation, we end up with something like this. Let's also make sure that this animation is using linear keyframes. So I'm going to hold shift and left click, grab our keyframes, select both of these, and let's set the function here to linear. Okay, just so we have a nice and even animation for our points appearing. So from here, let's drop this inside a solver, and let's step inside the solver, and I'm going to pin the viewport at the top level, so over here, and let's step inside. First, we need to bring back our coloring information for each frame, because currently if we play this, we no longer have our points turning to white. So let's do an attribute copy, and we will point to ourselves, which is the first input. So this will bring, this input 1 will bring the geometry from the top level, which has our points turning from black to white animations. So this will be our second input, and now if we play, we see we have our color information black, and now we can do certain things when the points turn to white. And what we are going to do is simply increment their age as soon as they turn white. So we are going to do, let's do this inside an attribute wrangle, just because it's easier to set up. And in the wrangle we will say that if your color, in this case I'm just going to grab the X component of the color, is bigger than 0, then I will say at age plus equals 1. And this is really the same way that we are going to set up the growth solver later down the line. But what this is saying is that when a point receives this white color, it's going to start incrementing the age for each frame. So if I go back, if I just zoom in here a little bit, and I go forward a few frames, when these 2 points turn white, they will have an age of 1, and moving on to the next frame, now they will have an age value of 2. A frame further, these 2 will have an age of 3, and these 2 that just turned white will have an age of 1. And then forward, these will have an age of 4, and then these will have an age of 2, and so forth until all of the points turn white. So what we can do with this age information now is, if I go up, I will drop down a blast node after the solver. I will set the group type here to points, and I want to add an expression, and I want to keep only the points that have an age value of 1. So here I will say at age equals 1, and I will delete not selected. And as a result, if I play the simulation now, if I play the entire animation, we can see that we have these flickering points that expand outwards, like so. And if I disable this blast node for a second, and what's happening here is that as soon as a point turns white, it will receive this age value of 1, but on the next frame it will have an age value of 2. So this condition will no longer be valid. And this condition will be true only for the first frame when any given point will turn white. And if I enable this blast node again, this is exactly what's happening. Maybe I can template our points like so, so we can see this. If I move forward a frame, now this point will receive a color of white and an age of 1. And on the next frame, this point will have an age value of 2. Because we are incrementing the age, so it will no longer have this value of 1. So this condition will no longer be true. And this is what's going to happen for all of the points. So now if I go to the result of the PopNet with our new emitting points, what we should see is that we are only spawning 1 particle per each point, and we are also going to have this nice evenly spread effect. So if I press play, here we have it. We can see the points that are closest to where we decided, where we added our point with this add node. These points are going to emit particles sooner in our animation, and then slowly progress further to the back of our helmet. Let's maybe also preview the geometry of our helmet. Okay, so we end up with something like this. And we can increase this offset in our emitter points if I increase the duration of this turning to white animation. So over here where we added our 2 keyframes that turn our points white, if I grab this keyframe, our second keyframe with the middle mouse click, I can drag this over maybe to frame 72, and now as a result we should, if I preview the PopNet, we should have an even bigger offset between our points appearing like so. So maybe I will actually leave this animation over 72 frames here. Now finally, if we go back to our set V attribute, let's maybe preview some points and turn on our display, which has our velocity visualizer over here. We will use this V to set our initial velocity. And we don't want this to be completely straight up, we want to be a little bit more specific. So I will create another add node. Let's go ahead and create another point. And I'm going to go ahead and grab this point and drag this over to the side and somewhere here in the back of our head. So I want the initial velocity to be from the position of our points, so the points that we are creating over here. We are going to create a vector that points to this add here. So let's place this in our second input. Let's step inside and let's get rid of this constant. We no longer need this. And from our op input 2, we are going to grab the position of our point. So it's going to be this one here outside. Let's go ahead and promote this to a constant of 0. And now from our position, we are going to subtract this position of the single point, and let's also do a normalize, and we will plug this in our velocity, and we can see that this needs to go the other way around. So I'll grab this subtract node and press Shift R to reverse the order, and now we have this vector that points to our point from the second input. Okay, and I can go up. Let's unpin the viewport here and grab our geometry and template this. Let's go back to our points, and we can now grab the second point that we created, and maybe we can adjust this a little bit. Let's do something like this. So now if I go back to the simulation, let's press play, maybe remove the visualizer, we can see that all of the points are heading over to this direction. Now, of course, for now they're not interacting with the helmet, so when we do this helmet interaction, the direction is going to change a little bit regardless, but we want to introduce for now just a little bit of noise so they're not uniformly going into the same direction. So I'm gonna go ahead and let's go back and select a frame here which has more points, or we can disable this blast node for now and just preview the velocity for all of the points. Let's go ahead and create a random vector for each of these points, which we can then add on top of the initial velocity that we set up here. So let's step inside. I'm going to go ahead and just duplicate our VOP global nodes here, and from the ptnum let's do a Gaussian random, and the signature here should be 3D float. Let's go ahead and normalize this. So this will create a random vector for us for each point. If I preview this, inside the velocity, this is what we have, and what we want is grabbing the initial velocity that we have, and I will simply do an add, and we will add the random vector to this. Alright, and now with a multiply, let's drop down a multiply, and I will promote the second parameter here, and I will also name this let's rename this label to rand, and if I go up, I can now control how much randomness I want to add on our initial direction. We also want some controls for the seed, so let's go back inside here, and to change the seed we need to add to this ptnum. So let's drop down and add before we set this inside a Gaussian random, and in order to get a completely different seed for each of these points, we will have to add a value that's at least as big as the total number of points. So we will grab our numpt, and this will be our second input, and also I want to multiply this value and promote the second input here, and this will be our seed. So let's type here seed, and if I go up, now we can use this seed value to generate random directions each time. So we will experiment with this and see exactly which seed will give us the best results. And now we can turn on our blast node, and if I go to the simulation, let's press play, and we have everything we need as far as our emitting points are concerned, and we can go ahead and focus on our pop simulation now. So now we are going to dive inside our popnet, which is going to be our first branch. In fact, I can just drop down in null to keep things organized, and we can rename this to first branch, like so. And let's step inside and see what we have to do. Maybe we can also just pin the viewport at the top level. So let's step inside here, and let's go to our pop source. For our birth options here, I'm just going to set the life expectancy to a value of 10. So this will roughly mean that the particles will last for the entire duration of this animation, which is 240 frames, which is going to be 10 seconds. Now the first thing that we have to do is stick our particles to this surface. So let's do a geometry VOP, and to reference our geometry, let's go up and let's copy the null of our geo-remeshed. Let's go ahead and Control C, and I will go inside our popnet back over here to the geometry VOP. And actually, let's rename this to stick to surface. And for our inputs, I'm going to place our remesh geometry in the first input. So I'll set this to SOP and paste the SOP path to our georemeshed over here. So now we can access this geometry from our op input 1. And from here we are simply going to do a minimum position, so min pos, and we will base this on our current position. So I will just grab the P, and now if I plug the result in our P, this is essentially like a ray that's set to minimum distance. This is simply going to find the closest position on the helmet geometry from where our point currently is. So this is roughly going to give us what we want. If I reset the simulation and press play, we can see now that the points are sticking to the surface, but the problem that occurs here, if I play the simulation more frames, we can see over here around the eye region, some of these particles get stuck, so they have quite a consistent speed, and then they reach to certain points in our mesh and they become stuck like so. And this is also apparent here. So for example, if I follow this point over here and we follow its duration, when it reaches sort of like these very concave parts of our geometry, the points sort of start to slow down by a lot. So what we want to do is maintain a sort of consistent speed and direction. This sticking problem that we are having with some of the points being slowed down in relation to the geometry is because even though we change direction for some of these points, when they reach certain parts, our velocity in fact is the same. So if I preview the velocity, we can see that we maintain the original velocity which we start with, even though the points are moving in really different directions. And if I were to disable this min pose operation for now, I'll just press Q on this, so our points are allowed to freely move. If I go backwards one frame, for example, and I go forward, and let's maybe go forward one more frame, and if we just look at this point over here, for example, the closest point on the surface that this point will find is going to be this surface here that's right on this edge here. So in reality, we will need this point to move across this gap that we filled over here, so where the eyes would be really. But physically speaking, the closest point on the surface is going to be on this edge. So this is why when we activate this, we can see we snap it to the edge, and even though our points are being pushed in this direction by the velocity, this minimum position is going to drag it down over on this side. And this is why we get this weird result. Let's maybe reset the simulation. And this is again why we get this weird result, with the particles getting stuck, especially over here and in the back as well. These particles really should be moving a lot further down the mesh. So what we have to do is update the velocity to get a new velocity that's more corresponding from where our point was on the previous frame. So I'm just gonna step inside Photoshop for a second to explain this. Let's say that this is our surface, and let's focus only on this point for now. We can see that our vector is going to pull our point in this direction. So let's say that on our next substep, the velocity is going to bring the point here. After we do our minimum position operation, our point is going to fall on the nearest point on the surface of the geometry, so maybe here, and it's going to end up over here in this position. And then on the next frame, we are going to keep the same velocity that we have, and it's going to do the same thing, and it's going to keep this velocity that we had on the previous frame. So it's going to be the same vector, alright? But what we want to happen is on the next frame, I want to compute this new vector that's being created after our minimum position. So I want our new velocity to be this vector right here, that's taken into account where it was on the previous frame and where it's landing after our minimum position. And this way, on the next substep, our vector is going to be pointing in this direction, which is going to be along the surface. And we are going to keep computing a new velocity that's going to be in relation with the surface, and this way we are going to achieve a smooth and consistent movement for all of our points. So let's go back inside of Houdini, and we know the position where our point is going to land in, and in order to reference the point from where it's starting, let's go up, and we are going to use this pre-solve input to grab the initial position. So let's do a geometry VOP here. Let's rename this to grab initial, and I'm just going to plug this here, and all we want to do is really record the position before we do any modifications to it. So let's go inside here and we'll just grab the P and we'll do a bind export and just create an attribute called init. So this will be our initial position. So let's go up. And this is the way the pre-solve and the post-solve operations work over here. So these two inputs. Over on the pre-solve input, we can do certain stuff and set parameters and attributes before we apply them to the actual point. So on the post-solve input is where we actually move our point with the velocity. And now what we can do is let's do another geometry VOP. Let's rename this to set new v, so set new velocity. We'll go inside. We'll grab, let's do a bind and grab our init attributes. So our initial position, this will be name init, and this has to be a 3 floats. And in order to create our vector, we are simply going to subtract our positions. So let's do a subtract here, and let's subtract the initial position. And now I also want to normalize this, so let's drop down a normalize and let's plug this directly inside our V and see what we get. Let's maybe reset our simulation and let's press play. Now we can see that all of the velocities are updating, and if we look at any given point, we are going to see that we maintain a velocity that's going along the surface. So for example, if I look at this point, when this point reaches this concave part, this rounded part over here, the velocity is going to adjust according to the surface. So let's just move forward, and we can already see this happening as it takes this corner. Now it's going to update the velocity like so. Okay, so again, we can just watch this point, but this is happening for all of the points. So if we watch some points over here, all right, so now they're freely sliding across the surface and they're no longer getting stuck in any of these weird rounded areas. And by doing this, we basically can use any kind of geometry for this effect, and it's still going to work with the same setup. Now, currently, if we play this, the speed of these points are a little bit too high, so we are just going to drop down a multiply here, and I'm going to promote the second input. Let's go up and let's set this to a value of 0.2. So we want these particles to go a lot slower, so something like this. Now, one final problem that we have to take into account here, we can see from the very beginning, if I just move forward frame by frame, on the very first frame where we create our point, I don't want this operation to happen, this set new velocity. I want to have the initial velocity that we set. So if I disable this, I want this vector to be on the very first frame when our particles spawn, in order to be able to sort of direct our particles to the specific point that we created here. So for our pop source, there is this, in the birth tab, there is this just born group, which creates a group for the particles that exist only on the first substep in which they are born. So let's rename this to just born. And then for our set new v geometry VOP, I want to exclude this just born group. So I will do exclamation point and type here just born, like so. Okay, so if I reset the simulation, let's just go frame by frame. Let's go forward. So on frame 4 we have our first points, and we will inherit the velocity that we set outside at the sublevel. So again, I'm just gonna go ahead and go up. This is the velocity that we want on our first frame in which the particles are spawned. So let's go back here, let's go inside, and then on the second frame, this new velocity computation will happen, and the points will be able to slide across the geometry surface like so. Okay, and we can see that really this new velocity that we are creating here is really just to take into account the curvature of our mesh a little bit more. So we can see that as our points start to take this corner here, if I look at just this point, we can see now that the velocity slightly changes to account for this direction change. Okay, and for the most part, if I play the simulation, we have a pretty consistent speed. We can see that as they pass, this nasty eye region, they no longer get stuck, and we still maintain a consistent speed. Now the direction changes slightly, especially these ones in the back. If I take a look, maybe some of these areas here on the geometry are kind of whack, so we can see what happens with our velocity. It has a little bit of trouble adjusting. This can be solved if we are going to smooth the geometry, our remeshed version, but really I think this will be fine for the most part. I'm pretty okay with some of the points going across, because by this point our main branches will already have been formed, and at this point we already have most of the transition happened already. As a final thing that I want to do here is maybe just add a little bit more variation in the speed. So over here we can grab our point number to generate a random seed. So let's grab our ptnum, do a random, and let's do a fit range on this and multiply our result. And we want to do from 0 to 1, let's try 0.7 and 1.3. So this should offer us plenty variation. Let's go up and let's press play, and this will just give us a little bit more of a organic result. Okay, so this will be fine for our first branch, and from here we can use these leading points to create the actual curve geometry. So let's see how we do this. Let's go up, and this will be our first branch leading points. Now we are going to use these to generate the second and the third branch leading points as well, but for now let's just focus on creating the curve geometry. For this I'm going to go ahead and grab this and just do an object merge and create a chain for each separate geometry over here down below. So let's do an object merge and paste our branch points over here, and really here what we can do is simply source all of these points inside another pop simulation, and the default behavior that we will get is going to create a trail of points left behind our leading points. So let's disable the visualizer. So let's do a pop network from here, and let's step inside. Let's go to our source and let's set the emission type here to all points, and let's press play, and this is the result. We have a little bit of problem because we are inheriting the velocity from our leading point. So in our attributes here, let's set the inherited velocity to 0. So really we just want to spawn points as our leading branch points progress along the surface. So the result will be this, and this is exactly what we are looking for so far. A couple of problems that we are having here is if we go up and if we look at our leading points, this object merge, and I press this information, we can see that we are inheriting all of these points. Now most of these attributes, if I go to this, most of these attributes are not going to bother us that much, but we are essentially overriding the age and the life attributes that our trailing points will inherit. So what we want to do here is just do an attribute delete, and we will remove the age and our life, so we can set a new age for our trailing points over here. So inside our birth tab, let's just set the life expectancy to a value of 1 and see what result we will get. If I go back here, this life expectancy is really going to be how big we want our branches to be in terms of length. So if I go up, let's press play, and we can see that after 1 second, so when they start emitting over here, after 24 frames, which is 1 second, now we will start deleting the points at the base. Okay, so obviously we want these to last a little bit longer. Let's go inside and let's try a life expectancy of 2. Okay, so now they are a little bit longer, and this is probably what we want. Maybe let's go for a final value of 3 over here, and just make sure that at least for our initial branches, for our first branches, they are nice and long. But probably a value of 2 for this effect will do just fine. I'll just leave this at 3 and readjust later if needed. Alright, so this is the result, and the way we can connect all of these points now and turn them into a curve is we can give each of our leading points an individual attribute that we can use after our pop simulation to connect all of the points. So all we have to do really is, if I go up after our attribute delete, let's do an attribute wrangle, and all of these points have an ID, and we want to store that ID as an individual identifier for all of these leading points. So all I'm gonna do here is say that let's create this attribute, and I will just name this to ID underscore orig, or we can also use ID rest, whatever is more meaningful to you. This is again just to store their current ID, so let's just do ID at orig, and we will set this equal to at the current ID. Alright, and if let's maybe just do a visualizer for this, because this will be more apparent. I'm going to visualize the ID orig over here. Let's turn on the visualizer, and I'll disable the V, and let's go here and make sure that this is a random. Let's do random from attribute ID orig. Alright, so all of these ID orig values have one unique color, and now if I go to the PopNet and I reset the simulation, we can see now that we inherit our original ID. So now all of these strands have the same color, and we can use this ID to create our geometry. So let's do an add over here. Let's set this to polygons by group, and inside this add operation, let's use by attribute, and attribute name will be this ID orig that we created, and now we have our trails. I'm gonna go ahead and press D. Let's go to the geometry and maybe increase the wire width so we can see this better in the viewport. Okay, and I can disable the visualizer for now. Hopefully this makes sense. We are just storing their original ID of our leading points, then all of our newly formed particles are going to inherit that attribute, and using that attribute we are going to connect all of the points. So this is what we end up with, and from here we can do a lot of stuff. So one of the things that I want to do is let's set the coloring for this. So I want the colors to be brighter near our leading points and then have a gradual fall off. So let's do an attribute val from here, and we can use the age for this. So let's step inside, let's grab our age, and we will do a fit range to further control this. Let's also plug a ramp parameter after, set this to a spline ramp, and we'll plug this inside the CD. I want to promote the source max for our age, and we can go up now and reset this ramp. And let's go ahead, and for our ramp I'll add another point here near our first point, and for this last one I'm just going to decrease this. Alright, so here we have this gradual fading, which we talked about. And now if we increase this maximum value from our fit range, we can spread this ramp even more. So we can see that as I increase this, we can use a maximum value of 3 here, which essentially uses the entire length of our curve, since our maximum age is going to be 3. So we can use 3 if we want, or we can make this shorter, and this will be completely up to you to decide. One other thing that I want to add here is add another point, and I'll grab these 3 points, so the second, third, and the fourth one, and I'll set the interpolation to B-spline. So we have this nice smooth decay over here, so it's really bright near the top, and then it's going to have this exponential decay over the rest of the curve, which just looks a little bit nicer. So we end up with something like this. Maybe we can grab the second point and bring this over so it's not completely dark over here. Alright, so this will be our color. Maybe we can rename this to set CD, and we want to do a similar thing for our p-scale. Let's go ahead and do another attribute vop. Let's rename this to set p-scale. Pretty much we can do the same thing. In fact, we can go ahead and just copy both of these nodes. Let's Control C. Let's step inside our new attribute vop, and I'll paste these here. And let's make sure that this fit range is connecting to our age. And what I want to do here from our ramp is do a bind export and export this to a p-scale attribute. And we also want to have an additional control here. I'll just do a multiply and promote our second input, and this will be a global multiplier. So let's just rename this label to mult. And I'll go up, and we'll do let's start with the same kind of ramp over here and set the maximum value to a value of 3. And for our multiplier, we want the p-scale to be rather low, so let's use a value of 0.01. And now to preview this p-scale, let's plug all of this inside a sweep node, which automatically recognizes the p-scale attribute. And I will set the surface shape to round tube, and we can already see that we have the geometry, and we have sort of this size already on our curves, but we have this this very weird twisting geometry thing going on, and this is because some of these attributes from our particles are messing up the orientations and stuff like that. So what we can do here really is let's do an attribute delete, and this is something that we should do either way to keep the geometry nice and clean. And let's go ahead and get rid of everything except the p-scale and our color. So we will select this here and do delete not selected. Alright, so now we have the correct result, and we can go back to our p-scale, and maybe I want to increase this global multiplier to 0.02. And we can also play around with this ramp. Let's do something like this, and maybe I want to make these thicker. So instead what I'm gonna do is probably the reverse of our color ramp. Let's grab these three handles again and set the interpolation to B-spline as well. So let's do something like this, and for the most part I think this is looking pretty good. Okay, as we preview this, I'm pretty happy with this result. So it's nicely flowing along the surface, and we are off to a very good start. And this is really how we can turn these into geometries and render them. Of course, we don't really need this sweep node when we do our renderings, so we are in fact going to turn off the sweep node when we import the geometry into Solaris, because in Solaris this curve will already render with the p-scale thickness that we defined over here. So we don't need to be using actual geometry. Solaris by default is going to turn the curve into a geometry at render time. So it's going to be pretty fast to render this, and we don't have to worry about any weird issues that might happen. So we are going to follow this same structure for our secondary branch. So this will be our first branch, and our secondary branch and our third branch is going to look something like this as well. And then we are going to be able to control individually for any of the branches the fading of our colors and our p-scale and stuff like that. So we are going to have a lot of control.